Thank you very much.
Ah.
So, 1 second. Thank you. So our research is developed for more than 40 years ago, and it starts, is not written here, regarding the manufacturing of biocomposite materials processed by powder metallurgy, which are used for bone addition or bone reconstruction. After theoretical researches and then a little bit of practice, we decided to continue because we had good results. So in 2014, we started by a research project in Romania with colleagues from Polytechnica from Bucharest University, some hospitals from Bucharest, Institute of Physical Chemistry from Bucharest. So a multidisciplinary team in order to develop new materials for this kind of application. After we succeed good results in 3 years, we continued up to this moment with another partners. So you see the circle is growing. So we believe that our results are good, and we intend to look for future partners for future development. What we have been done up to this moment? Actually, this conference is the first conference where we saw, I was impressed about the final questions after the abstract. What will audience learn from the presentation? And from this perspective, I organized the entire presentation on what for real the audience will learn from this short presentation. So first of all, we will be focused on the application. Then what is about this hard tissue engineering? Who can benefit on this? Normally the medical doctors and the biomaterials engineers, but from different perspectives regarding the product shape and then the product performances. Then future trends in research and education. And we will be focused on artificial intelligence, on augmented reality and virtual reality, and then how can the students be much involved in research in this area. Regarding the application, this kind of materials are dedicated to bone reconstruction and addition, and we are all aware about the metallics, ceramics, and the polymers and polymeric composites, which are dedicated to this purpose. Also, there are a lot of processing technologies, more or less complicated and complex. And we were very attracted on this one, on the powder metallurgy, because it is providing a lot of advantages regarding the selection of the powders, the initial powders, the selection of the powder size, the reinforcing content of the composite. So we believe at the time that we can develop a new route to process such materials. So we decided to work with this system, which actually it's quite well known, hydroxyapatite and titanium hydride. We selected it because it has a good and a very attractive property regarding the foaming process. So during the heating, this hydrogen, as you will see, will be released. So we can monitor the porosity of the material from this point of view. Because everybody knows in biomaterials field that the bone is not an isotropic material, is quite anisotropic. So we need to play somehow with the porosity, to play in order to obtain biomimetic structure related to the cortical tissue or to trabecular tissue. So the matrix was from hydroxyapatite. We tried two kinds of powders, nanometric and micrometric hydroxyapatite particles, which were mixed with titanium hydride powders, which were micronic. After the mixing, we tried also to improve the porosity, including other foaming agents, calcium carbonate and ammonium carbonate. The technology is quite simple, just mixing, compaction, and then sintering. But due to the combination of micronic and nanometric particles from one side, and due to the different kind of foaming agents, we obtained different anisotropic structures, as you will see. Actually, as you see here, we obtained a cortical tissue structure quite similar to the genuine one, and also a trabecular tissue, having the properties as there are written here. So the density, porosity, quite related to the genuine structures. More than that, these materials provided very good dry friction coefficient after dry friction tests and also in wet friction conditions. And the wear rate, as it is written here, is quite comparable with those with that similar to the more complex biomaterials obtained for the same purpose. So we proved that this technology, which is quite simple, allowed us to obtain such complex structure with comparable properties of the materials obtained, similar to those produced by another technologies. Actually, in which are the which is the core of this technology? Because we have nanometric hydroxyapatite mixed with micrometric titanium hydride, we try to select those sintering treatments which allows us to keep the nano feature of the material. So we want to keep the nanometric hydroxyapatite after sintering, because, you know, during the sintering, a classic sintering, which is for the ceramic-based materials quite a long process, this conventional sintering will lead to the increasing of the grain size. So in this case, we try to select new sintering techniques, and we were focused on microwave sintering, spark plasma sintering, and two-step sintering. All these three we tested allowed us to obtain a nanostructure biocomposite to keep the hydroxyapatite in the nanometric range, and the titanium hydride developed, as you will see. So finally, we decided from these three new sintering techniques to select this one, two-step sintering, because it develops in a conventional furnace, which is a normal conventional, it's a conventional sintering furnace. As you can see, as you know, spark plasma sintering means very developed technology with special tools, which are quite expensive. Microwave sintering, we have some problems to control the temperature. So we said, let's try this two-step sintering. And we obtained quite beautiful results. This technology consists in heating of the powder of the green compact to a temperature a little bit lower than the conventional sintering one. and then suddenly very quick cooling up to a range temperature, and then a slow cooling. Actually, if we split this treatment in those two steps, more detailed, we observed that during the first step, which the end represents the initiation of the sintering diffusion, of the diffusion between the particles, actually during this step, we had also three simultaneous foaming processes, meaning the titanium dihydride decomposes in 3 or 4 steps up to titanium and hydrogen, which is releasing, that means bubbles and that means pore. This process develops between 400 and 800 Celsius degrees. But before this range, temperature range, we have the ammonium carbonate, which foams at around 60 Celsius degrees. And the last part of the first step is dedicated to the decomposition of the calcium carbonate, which goes to calcium oxide and CO2. So if we monitored these processes in the samples with micronic hydroxyapatite and nanometric hydroxyapatite, and we had a nice book chapter about this, all these processes developing in the first step of the two-step sintering process. So at the end of the first step, we cooled down very quickly the samples, and we kept to the second thermal range, which is known in the material science and engineering as a kinetic window, which controls the grain boundary diffusion versus the grain boundary migration. So controlling this temperature, temperature 2 of the second step, and the time of this dwell, you can play with the nanometric structure and with the porosity related to the first step, as you saw. So we identified different kind of porosities of the samples with the matrix, nanostructured matrix hydroxyapatite and micrometric hydroxyapatite using different kinds of the foaming agents. And we obtained very good results, meaning if you control this temperature and time, you can have good monitoring of the matrix from nano level up to micrometric level. The materials we obtained, they may be produced in different shapes. First of all, we proved that we may have a regular geometry of this biocomposite. The product finally has the name of alloplastic graft, meaning an engineering graft, which is placed into the genuine bone to repair it. Also, this material is able to be adjusted geometrically by laser beam, and also we have very nice structures and shapes. But most of the time, you may need an irregular geometry of the alloplastic graft, because the bone defect is not all the time regular as geometry. So we developed another route, medium pressure injection molding of these materials, and we had demonstrated that we can obtain nice structures, isotropic and also anisotropic, from the same mixture hydroxyapatite, nanometric, and titanium hydride micronic. Also, the colleagues from another institute, from the lasers in Bucharest, they obtained nice coatings by the technique of maple, nice coatings of these biocomposites on the titanium substrate. So we can develop this kind of product. Future research is oriented for this biocomposite as granules for bone addition, especially for the dentistry applications. Also, we had nice results regarding the biocompatibility of this material. We have developed in vivo and in vitro tests. So we had nice published papers about this, the behavior of our material regarding the biocompatibility. And not the least, there are some already published papers by other colleagues which proved that the artificial intelligence is able to help the monitoring of the osseointegration process. Normally, if we want to see how the minerals and all the substances inside the corp will cover the alloplastic graft made by our biocomposite, usually the patient is exposed to radiation for the radiography and so on. But usually there are, in the last time, there are developed already, there is a machine learning approach for a systematic mapping of what it happens with the interface between the biocomposite, the implant, and the genuine bone. Also, there are developed convolutional neural networks, which help us to see what is happening during the real connection between the implant and the bone. So the artificial intelligence is quite a new research area we can use for this kind of application. Not to mention the augmented reality and virtual reality, which is a very good instrument for the students and researchers in medicine and tissue engineering. They may learn how to work virtually, first of all, with this material, and then to use for real. The students can be involved. We have here nice modeling and simulation about the how we can use this material. We modeled a pilot in a car, and the pilot has here an implant, and during the frontal impact with the wall, as a standard Euro NCAP, it is proven that this material is very good and the head has no collision and no damage. We are looking for partners to develop next research in this area. So we are very happy we have the occasion and the possibility to speak to you and to show you what we can do, maybe with your help. Our team is thanking you for attention and looking forward for cooperation. Thank you very much.
Thank you, ma'am. Thank you, ma'am. Thank you for your wonderful section.
Thank you very much also.
It is open for discussion. Any questions? There is any questions to be asked?
Maybe we can keep the contact by emails. We have the
Okay.
data
Ma'am,
from
I
the
have
colleagues.
one question. So we have done a bone scaffold synthesis with the help of polypropylene fumarate and with the polylactic acid. So
Yes.
what will be the difference between this what we are synthesized the compound? It will be highly porous, and
I'm afraid I cannot understand you very well. If it is possible, please send me an email,
okay.
and it will be a better understanding.